Okay, this is going to be the homework solution for problem number 11-24. This problem is on double pipe heat exchangers. Okay? So what we are given is that there is this double pipe heat exchanger. Here I'm drawing the cross section. Okay? On the inside there is refrigerant 134A, and on the outside, or in the annulus, we have water. And we are given some information in the problem statement. We are told that the outside diameter, D0, is equal to 0.025 meters. We also know the inside diameter, DI, and that's going to be equal to 0.01 meters. We're also told that the mass flow rate of the water is equal to 0.3 kilograms per second, and that the temperature of the water, let me erase that for a second. The temperature of the water is going to equal 20 degrees Celsius. And there is a heat transfer coefficient on the inside of the surface, or in the inside pipe, and we're given that that H sub I is equal to 4,100 watts per meter squared Kelvin. And with all this information, we are asked to find out what the overall heat transfer coefficient is for this heat exchanger. We denote that by this capital U. Okay, so let's get started. First thing is we are going to have to assume that we have fully developed flow, so both hydrodynamically and thermodynamically developed. So we're not going to worry about any entrance region effects. The problem statement tells us that it is a thin-walled tube. So because it is thin-walled, that allows us to assume that there is no conduction resistance across the thickness of this pipe, because that thickness is very, very thin. So that means no conduction resistance. Okay? And also that wall thickness is so thin, that also lets us know that the surface area on the inside is also equal to the surface area on the outside. Okay? So that, knowing that, we know that the reciprocal of our overall heat transfer coefficient is going to be approximately equal to 1 over H sub I plus 1 over H sub 0. Okay? And so we were given H sub I, so the only thing we need to do to find out what U is we're going to have to go ahead and try and solve for what H sub 0 is. Okay? So that is the heat transfer coefficient that you get from the flow in an annulus. So this is an annulus flow. And when we're doing annulus flows, we have to, because it's a non-circular geometry, the first thing we'll have to do is find out what our hydraulic diameter is. And we denote the hydraulic diameter by D sub H. And for an annulus, we know that that's equal to the outside diameter minus the inside diameter. So for our problem, that's equal to 0.025 minus 0.01. So our hydraulic diameter is going to equal 0.015 meters. Okay. Now that we have the hydraulic diameter, we're also going to need to find out what our average velocity is. Okay. So continuity equation, our mass flow rate is equal to rho times V times A. So we can rearrange continuity, and we'll get that our average velocity is going to be equal to the mass flow of the water divided by the density of the water times the cross-sectional area of that annulus. Okay? So now we notice that we're going to have to get some properties for our water because we need rho. So let's go to the back of our book, and we're told that we have water and that it is at a temperature of 20 degrees Celsius. So if you go to table A-9 in the back of the book, and you look up the properties of water at T equals 20 degrees, you will find that the density is equal to 998 kilograms per meter cubed. The thermal conductivity is equal to 0.598 watts per meter Kelvin. And the dynamic viscosity is equal to 1.002 times 10 to the minus 3 kilograms per meter times second. And we'll also find that our Prandtl number is equal to 7.01. Lastly, we'll need to calculate what our kinematic viscosity is, nu, and we know that that's just equal to our dynamic viscosity divided by our density. So we'll take the 1.002 times 10 to the minus third and divide that by 998, and we will see that this is equal to 1.004 times 10 to the minus 6. Okay? So let's go back now that we have our density, and we'll solve for our average velocity. So we know our mass flow rate was given to us, and that's equal to 0.3. We'll divide by our density, 998, times our cross-sectional area. And our cross-sectional area for an annulus is 1/4 times pi times the outside diameter squared, so 0.025 squared, minus the inside diameter squared, 0.01 squared. Okay? So we calculate that, and we find that the average velocity is equal to 0.729 meters per second. Okay. Now we have our average velocity. We're always going to need to calculate our Reynolds number based on our hydraulic diameter, because we need to find out whether or not our flow is laminar or turbulent. So we know that Reynolds number is V average times the hydraulic diameter divided by the kinematic viscosity nu. So this is equal to 0.729 times 0.015 divided by 1.004 times 10 to the minus 6. Solve that, and we find that our Reynolds number is equal to 1.089 times 10 to the 4, and this is much, much greater than 4,000, meaning we have turbulent flow. Okay. So we know that when we have turbulent flow for a non-circular cross-section, we're allowed to use the circular correlations, but all we need to do is substitute out the diameter of a tube with this hydraulic diameter, okay? So we go into our book and we find the correlation for the Nusselt number for a turbulent flow in a pipe, and we find out that the Nusselt number is equal to 0.023 times the Reynolds number to the 0.8 times the Prandtl number raised to the n, where n is either 0.3 or 0.4 based on heating or cooling. So in our problem, the fluid of water is being heated, and therefore n is equal to 0.4. So we'll go ahead and plug in, and we'll find the Nusselt number is 0.023, Reynolds number 1.089 times 10 to the 4, raise that to the 0.8, multiply by our Prandtl number, which is 7.01, and raise that to the 0.4. And that we calculate, and that is equal to 85. Okay, so now we have what our Nusselt number is, and we know that the Nusselt number is just a non-dimensional heat transfer coefficient, so we can use the definition of our Nusselt number to find out what our heat transfer coefficient is in the outer annulus. So H0 is going to equal the Nusselt number times K divided by the hydraulic diameter. Of course, this is just a rearrangement of the definition of Nusselt number. So we plug in our values. We have the Nusselt number is 85. Our thermal conductivity is just a property. We looked up in the back of the book, and that was 0.598. We divide that by our hydraulic diameter, which is equal to 0.015. So we get that the heat transfer coefficient is 3,389 watts per meter squared Kelvin. All right, so now we're given the heat transfer coefficient in the inner pipe, and now we've solved for the heat transfer coefficient in the outer annulus, so we can go ahead and now calculate what our overall heat transfer coefficient is for this heat exchanger. We know that 1 over U is going to be approximately just 1 over HI plus 1 over H0. So this we'll plug in. We'll have 1 over U, approximately 1 over 4,100 plus 1 over 3,389. We go ahead and we solve this. Single equation, single unknown. We solve this for U, and we find out that U is equal to 1,855 watts per meter squared Kelvin. Okay? And that's the solution for problem 11-24.